Hey guys, welcome to this video on the normal distribution. In this video we're going to go through what the normal distribution is. It should be a bit of a recap from last year, but just in case we'll make sure we cover it again. Also going to go through the normal probability density function and what that looks like. So let's start off with, what does the normal distribution look like? Well, you may remember from last year a curve, we may have seen it, that looks something like this. It's not the best drawing that I've ever done of it, but you kind of get the idea. Well, in the middle here we have our mean, and either side we'll have points here where it's the mean plus one standard deviation. And likewise, the part over here will be the mean plus two standard deviations. So I'm just going to use that plus 2s. Well, realistically, we should be using this symbol. And likewise, it's the opposite over this side, where it's our mean, take one standard deviation, and likewise the mean take 2, etc. And we do have percentages that are associated with each of the areas that we have in here as to how much of the data will lie under each section of the curve. Let's look quickly at the probability density function. It looks something like this. Alright, so we've got f of x is equal to 1 over the standard deviation multiplied by the square root of 2 pi multiplied by e to the power of minus a half x take our mean divided by the standard deviation all squared. So it is quite tricky, but what this actually gives us is the value of, or the height of, our standard normal curve for our normal distribution. So if I'm to draw up another one and hopefully get it a little bit better, it's a little bit better but not overly great, then the point here, our highest point, is actually going to be our mean for our x value, 1 over our standard deviation multiplied by 2 pi. Now, why is it the fact that it's our mean for our x value, so we know that, but why does it, so why does this bit here be our value of y, or f of x? So we could actually put this onto a set of axes where we've got x and y. Well, the y coordinate here, if we look back up to our probability density function, then we've got the mean minus the mean, which would make this entire thing, so mean minus mean, which is 0, 0 over, doesn't matter what it is, squared, will make this entire thing 0, so this e to the power of minus a half times 0 becomes e to the power of 0, makes it 1. So we can actually go through knowing the standard deviation and the mean, we can work out what the height is of our probability density function, or the normal curve. So what does that mean? This will start to make sense when we look at it in terms of integration. So if we've got from minus infinity to infinity of f of x which is our probability density function with respect to x, well, this is going to always equal 1. So you may have seen, as I mentioned previously, that, say, this part here and this part here, they both equal 34.13%. This is where that 33.13% comes from, because we can actually look at from one standard deviation to the mean, and or up to one standard deviation either side of the mean, and we'll find out what our integral of, or the area underneath the curve equals, which we'll find to be the 34.13 for each of these as a decimal. And actually, I'm going to write down what the first and second derivatives of this function look like. So, the first derivative looks something like this, where it's minus 1 over our standard deviation squared, 2 pi, x minus our mean over our standard deviation, e to the power of minus a half, x minus our standard deviation over, x minus our mean, sorry, over our standard deviation, all squared. So that means for f of x to be equal to 0, well, looking at this part here, then when x is equal to our mean, our function will equal 0. So we know that at the point where x and the mean are the same, we're going to have our maximum point here. Likewise, if we look at our second derivative, our lovely long-winded thing here. Now, it is worth noting that this part here is the e to the power, where this part here is actually back down again. If you look on page 233 of the textbook, it sets it out a little bit easier. So, in this case, when f of the second derivative is equal to 0, we know that this is a point of inflection. So, we're going to have points of inflection at when x is equal to our mean plus or minus our standard deviation, which we know already. Well, might not know, but we might have recognized it. Alright, so let's move on to a bit of an example. If you can, please make sure that you get this formula written down. So pause the video, get that written down, and then we will move on. And also get this bit here as well. Alright, so hopefully you've got that written down. If you don't, please go back and get it. So up here I've drawn what our normal distribution looks like, and I've associated the percentages with each of the different areas underneath the curve. For example, between our mean and our mean minus 1 standard deviation, as I've mentioned before, it's 34.13. And when we integrate, we'd find that, as I've mentioned previously, that the area under there would be 0.3413, roughly. If we go and actually work it out, it'll be a bit more than that. So that means that between our mean plus or minus 1 standard deviation, we're going to have 68% of our data is going to lie there. Between 2, we're going to have 95, and between 3 standard deviations, we'll have 99.7% of our data. So, if we want to look at an example now, let's do that. So, the chest measurements of an 18-year-old male footballers are normally distributed with a mean of 95 centimetres and a standard deviation of 8 centimetres. So what does this mean? Well, our 95 here is going to be equal to our mean, and our standard deviation is equal to 8 centimetres. In this case, I'm only using a sample, I'm not using the population symbols. So, find the percentage of footballers with a chest measurements between 95 and 103 centimetres. Well, if our mean is here at 95, what we need to do is work out what are the values for 1 standard, 2 standard deviations, 3 standard deviations away. And in fact, this should be a plus. So 95 plus 8 gives us 103. 95 plus 8 gives us 111, 119, and etc, etc. So if we go, in this case we've got 87, 79, and 71. So what percentage lies between 95 and 103? Well, that's between this point here and this point here. In this point, we've got 34.13%, and that's our answer. What if we go between, if you decide to survey 200 footballers, how many would you expect to have a chest measurement between 87 and 111? So we're going to look between here and here this time. So let's add up all the percentages. So we're going to have 34.13 plus 34.13 plus 13.59. And all of that added up together gives us 81.85. Now, the question asks, from a group of 200, how many would you expect? Well, we've got to find out 81.85% of 200. And the easiest way to do that is go 200 multiplied by 0.8185, which will give us roughly 164. This number here that you're going to generally come up with will be more than not have a decimal, so just round it to the nearest value. The final question, find the value of K such that approximately 16% of the chest measurements are below K centimetres. So we're trying to find somewhere over here a point K that will add up to 16%. And if we look at it, if I was to draw it out quickly, then we're looking somewhere here that this is going to be K and our mean will be here. So we're looking for a point where this will be 16%. Now we can just look at our normal distribution here and see that if we go 0.13 plus 2.15 will give us 2.28. 2.28 plus 13.59, 15.67%, which is roughly 16%. So we could say that therefore K is 1 standard deviation below the mean. Therefore, K is going to be equal to 95 minus 8, which is just equal to 87 centimetres. So we'd expect that roughly 16% of all the footballers are going to have a chest diameter of less than 87 centimetres. Alright, I'm going to leave this video here. In the next video I'm going to show you how to do these using a calculator. Hopefully you've got something out of it. If you've got any questions, just ask. I do apologise for it being a bit of a long one. Thanks for watching. If you've got any comments, just please feel free to let me know. And as always, we'll see you next time.